Let's compare a end-fed half-wave antenna to a center-fed dipole, this time on the channel. I've been seeing a lot of questions on YouTube chats and on various forums comparing an end-fed half-wave antenna to a center-fed dipole of some sort. And some of the questions are, would an end-fed half-wave antenna work as an NVIS antenna? Does the pattern of an end-fed half-wave look the same as a center-fed dipole? And I thought I'd make a quick video and do some modeling to kind of clear that up.
I'm going to apologize up front. I'm getting over a cold, and if it sounds like my head is inflated to 300 psi, it's because it is. So hopefully it won't be too nasally. So the software I'm going to use to model these antennas is EZNEC. So EZNEC. And this software is a free download. The author of this software, Roy Llewellyn, W7EL, and he graciously a few years ago decided to give this away for free. And it's a very powerful program. I encourage any ham or anybody that wants to design and build an antenna to download, install this software, and learn how to use it. It's a tremendous resource. Hats off to Roy for doing this because it's very powerful software and it's free of charge. So anybody can download it and use it. Now, I've already downloaded this and used it, so we're not going to go there, but let's go ahead and open up the program. And when you open it up, your main window is antenna parameters. And in order to see what you're building, what you want to do is hit View Antenna. Now, these instructions are going to be kind of quick and not very detailed because all I want to do is just kind of hit the ground running here. But essentially, you're going to build an antenna using coordinates. And these coordinates are units, and the units can be inches, feet, meters, millimeters, wavelengths, whatever you want to work with. I tend to go with feet for HF antennas and inches for VHF and UHF antennas. Meters would probably make more sense, but all of my huge tapes, my big tapes, are graduated in feet and inches. So I tend to work with that, and I'm just familiar with it. So we're going to work with feet today. And I want to build and model both an end-fed half-wave and a center-fed dipole. And then we're going to model the patterns for those antennas and see how they compare. That's the purpose of this video. We want to see if some of the chatter that's been going on that I've heard lately is true or false. And I'll give you a little bit of a spoiler alert. With most things in ham radio, it depends. So on a lot of factors, but we'll get to that in a minute. So anyway, we're going to model this antenna in feet, and if you're building a really, really complex antenna, you probably want to start out modeling in free space because that way you don't have to worry about ground interactions at all. This software will not allow you to model wires below ground level. There are upgraded versions of it that will, but this particular free version will not. So if you have a really complex antenna, then it's best to model it in free space and then put it over ground when you're ready to actually look at patterns and gain and SWR and that sort of thing. But since this is going to be just a simple horizontal dipole, I'm just going to go ahead and throw it 30 feet above the ground. It's telling me it's zero length, so we can fix that. Let's make it, let's see, we'll make it 67 feet long. And now it's telling me that segment length is too long. The segment length is determined by frequency. So each one of these segments in the antenna, the software will compute current voltage along its segment length. and then just compile that information for the entire antenna. So you always want to make sure that when you're building the antenna, one of the first things that you want to do is come up here to the frequency, and you want to change this to the frequency of the antenna that the antenna is going to be operating on. In this case, I'm going to really quickly build a 40-meter dipole. So I'm going to set this up for 7.2 megahertz. And it's still telling me that the segment length is too long. It says the length is 7.44 feet per segment, and our maximum should be about 6.83 feet. Now you'll notice, let me undo that. See how that changed? When I had the frequency set for 440 megahertz, it was telling me the recommended maximum length was 0.2682 feet. And that's because at 440 megahertz, the entire antenna is going to be pretty short. So the segment length is going to be very short. So you have to type in your frequency before you start doing anything else. And like I said, 7.2 megahertz is where I want to be. Okay, so now we have this dipole that's 30 feet above the ground. It's about 67 feet long. And I'm just going to check the SWR. Oh, wait a minute. I have to change my segments first. Let's see. Let's go with 33. I'm going to put more in there than I really need because I'm going to be center feeding it. That gives me a little bit of leeway on how short of a movement that source can be moved if I have more segments. I'm using 14 gauge wire. You can put in your wires as a number gauge. So number 14 gauge, number 12 gauge, number 20 gauge, etc. Or you can just type in a number like 0.250 if you're trying to model something like aluminum tubing. In this case, I tend to work with wire more than any other building material, so number 14 wire is my go-to. So let's go ahead and check our SWR. And before we do that, we have to install a source. I'm going to put the source in wire number 1. And I'm going to put it right in the middle. This is going to be center fed to start with. And you see it actually gave me 50%. And the reason it was able to do that is because I have an odd number of segments. If I would have changed this to an even number, it wouldn't be 50%. Let's change this to 32 and see what happens. See how the number changed up here? Now we're at 48%, 48.4375%, because I don't have an odd number of segments. So we'll keep that an odd number. That way I can split this antenna perfectly in two. Now another way to do this is just create a very short segment or wire just for the purpose of putting your source where you want it. And I tend to do that with ground planes. I'll put a little short wire right at the base of the ground plane and put my source on that, and then I'll put another wire on top to continue up with my vertical section of that antenna. Just makes it more precise when you're trying to get the source exactly where you want it. But in this case, it's just exactly in the center, so we'll leave it there. Okay, now we should be able to model this thing. And I'm going to keep it wide to start with because I don't know how close I am, so we'll go 6 to 9 megahertz. I'll use 0.1 as the step, 0.1 megahertz, and we're going to run that. Okay, I got pretty close. That's 7.1 megahertz right there. So we'll leave it alone. And I'm going to go ahead and plot it. So I'm plotting in 3D. You see how this is just like a big ball, 3D ball here. You can plot in different methods. You can plot in elevation, like so. And you can also plot in azimuth. When you're doing azimuth, you need to put in some sort of an elevation angle. 5 degrees is a good one to use because that's what a good DX antenna should be built to. And then it'll show you the top view looking down on the antenna. So I usually use 3D simply because when you're using 3D, you're kind of getting the best of both worlds. You can see everything. And not only that, but you can also pull up an elevation view. They give you this option where you can do that over here, show 2D plot. So not only can I see what the big ball of RF looks like, I can also move that pointer around. I like to move it down here to 5 degrees if I'm building a DX antenna. I just kind of move the cursor around to see what it's doing at different angles. Okay, so what we should notice right off the bat is with this antenna being 30 feet above the ground, as is a relatively low HF and low frequency HF antenna is going to do, it's going to put most of your gain straight up at 80, 85, 90 degrees. This is kind of your classic NVIS antenna, what people call an NVIS antenna, which is actually a military term that us hams have sort of borrowed, which means near vertical incident skywave. And the purpose of it is for local communications on 40 meters and lower. So 40 meters, 60 meters, 80 meters, 160 meters. Those are the frequencies that work very well for local comms. So anywhere from 70 miles out to about 1,000 miles is what I consider NVIS. And you can do that on 40 meters. 80 meters is probably a better choice, especially at night. But that's typically what you would consider an NVIS antenna, is between 70 and 1,000 miles. The DX antenna, I consider those, it's just my opinion here, but I consider those to start at 1,000 miles and go up from there. So this is a pretty good NVS antenna. Your gain is straight up. It's got pretty good gain, 6.11 dBi. And the reason for that is we were not able to get this antenna a half a wavelength above the ground. If we put it up at 67 feet, let's see how the pattern changes. That's a little different, isn't it? Now what we have at half a wavelength above the ground is a very well-performing DX antenna, long distance antenna. Our gain went from about minus 9 dBi to minus 2.99, call it minus 3 dBi. So the gain way down low on the horizon is much, much better. You can see instead of wasting all that RF straight up in the air, we've squashed it. We've concentrated it in two directions. So behind and forward. It's the same amount of energy, it's just pointed in a certain direction now. So that's the key for DX antennas, getting it up at half a wavelength, or is it? So let's hash this out a little bit further. Let's take this back down to 30 feet. Now, so far, we've just been dealing with the center fed antenna. And center feds make great NVIS antennas, but can you do the same thing with an end fed? Is it possible to do the same thing with an end fed? Well, let's find out. We're just going to change our feed point, and we're going to make it, let's try 4% to start with. Let's see if that works. Now, an end fed antenna is going to use a 49-to-1 transformer, and our effective feed point impedance is going to be about 2450 ohms. And you'll see they give you an option here to get creative with your feed point impedance. Right here it's 75 ohms. We need something a little bit bigger than that, so I'm going to change that. I'm going to come over here and I'm going to put in 2450 ohms. And now this gives us a realistic SWR with a 49-to-1 transformer right at the feed point. And you can see it looks very much like the center fed, not much difference at all. And when we model it, what do you know? 6.09 dBi instead of 6.19 or 6.11, was it? 6.11. And down here at 5 degrees, we're at minus 10. The other one was minus 9 something. So very, very close. You definitely wouldn't be able to notice it on the S meter. So the patterns between an end-fed half wave and a center-fed half wave are almost identical. Really, the only thing that's changed is the feed point. But there's more information that we need to consider, because the reason that NFEDs are so popular is they're a multiband antenna. They're not just resonant on their fundamental frequency, they're resonant on many frequencies. So we're gonna switch this up a little bit. We're gonna go from 7 megahertz and we're gonna take it up to let's go to 33 megahertz. And we have a nice multi-band antenna. We saw our SWR at 7.1 megahertz, but we've also got a nice dip at 15 megahertz, a nice dip at 22.7, and a nice dip at 30.5. Now, you could modify this thing to get it in the middle of the handbands, but I'm not going to do that. I'm just here to prove a point. And that point is that the difference between an end-fed half wave and a center-fed half wave on their fundamental frequencies, whatever it's cut for, in this case 40 meters, there is no difference. They perform exactly the same. But there is a difference when it comes to harmonics. So if we check this thing at its harmonic frequency of 33 megahertz, we see something different. Now we're seeing some gain low to the horizon, and this thing, it's starting to look a little bit like that antenna that we had at half a wavelength, isn't it? And there's two reasons for that. Reason number one is when you're modeling something at 33 megahertz instead of 7 megahertz, you're way more than half a wavelength above the ground. So gain comes from that. But also, when you're dealing with an antenna that has multiple current lobes on the same piece of wire, you get gain and you get lobing off of that antenna, such as this pattern right here. You can see that we have gains and we have nulls. So there's minus 5.7 dBi, but as we come into that lobe, now we're plus 10.65 dBi. And now we have a null, and that's at 15 degrees. Let's go back to 5 degrees, which are a reference for a DX antenna. And you can see we have serious nulls there, minus 5.66, and we're coming out a little bit above. But essentially, this antenna does have gain, and it has nothing to do, or not much to do, with the height above ground. It's got more to do with the fact that it's a multiple wavelength antenna. And we can prove that, because let's go ahead. We modeled that 40 meter antenna. Let me go back to that. Let's go 7.1 or 2. And we'll look at that model. And we already justified our gain is at 90 degrees or 80 degrees, straight up in the air. And our height above ground is 30 feet. So now let's look at an 80 meter end-fed. So we're going to make this an 80 meter antenna instead of a 40 meter antenna, but the height above ground isn't going to change, and our frequency isn't going to change. And we're just going to model it. So we're still transmitting, receiving on 7.2 megahertz, but look at the difference in the pattern. It's completely different. We have these two huge lobes, and they do have somewhat of gain when it comes right down to it. At some points in this pattern, it's slightly better than the 67-foot antenna was, but it's mostly worse everywhere else. So this is actually the worst possible current distribution on a dipole. This is kind of what you want to stay away from, is two current maximums on a piece of wire. Because this, well, whether it will work, this antenna will work, but there is better configurations that will work better than this would. So this is kind of the one you'd want to stay away from. But the point is, that I've heard people say that an NFED half wave makes a good NVIS antenna. This one is not going to be a good NVIS antenna. If you had a 67-foot wire here at the same height of 30 feet above ground, it would be much better at NVIS. And I've proved that to myself. I've built antennas that tried to concentrate gain at like 75% off the horizon and compared those with antennas that had gain at 90% above the horizon. And the 90% above the horizon antenna would perform better. So this, having these two current lobes would not be a good NVIS antenna at all. But on 80 meters, it would work just fine. Let's go 3.8 megahertz and see what the pattern looks like there. So now we're back on a fundamental frequency, and you can see we have a single current maximum on the antenna, and our gain is back at 90 degrees. That's 5 point something dBi. It's not too bad. So at 80 meters, the NFED half wave would be a good NVIS antenna. So point number one is an NFED half wave antenna is only good for NVIS on its fundamental frequency, whatever that happens to be. On any other frequency, it's not going to be good for local comms. It's going to be okay for DX, especially if you want to compare a 40 meter length of wire at 67 feet to an 80 meter wire at 134 feet-ish at something like 33 megahertz. Let's see what that works out to as far as gain. So now you can see we have a whole bunch of current maximums on this long wire. And we have really good gain down low to the horizon, 7.38 dBi. So this would actually be a pretty good DX antenna at that frequency. Now this isn't 28 megahertz. I'm guessing on this. Let's see if I'm right. Yeah, 30 megahertz. That was close. So this one actually needs to be a little bit longer. Let's make it 137 feet. Let's see if that helps us at all. Okay, 7.3, 11, 14.8. Might still be a little bit high. 18, 22, 30.1. Let's make it a little bit longer yet. Let's make it 140 feet. Okay, 7.1, 14.6, 29.4. We're getting closer. So one of the disadvantages of an NFED half-wave antenna is if you tune the bottom frequencies to be right on, you'll typically be high on frequency at 10 meters, 20 meters, etc. And there's ways to do that and get around that problem. And what I usually do is I'll tune it a little bit low on 40 meters, like 6.9 megahertz. And that kind of brings all the other ones in line. You can also put, I think it's 100 picofarad capacitor in the 49 to 1 Ballon box, and that helps tighten things up too. But I digress. So anyway, is an NFED half-wave just like a center-fed dipole? Yes, but only on its fundamental frequency. Is an NFED half-wave antenna good for NVIS? Yes, only on its fundamental frequency. If it's on a harmonic, whether it be even or odd, it doesn't matter. It isn't a good NVIS antenna. And that's basically it. So I hope that clears up some of the noise. And I hope that you download the software and use it. It's really, really good software. Typically when I'm building an antenna, what happens, the process is I get an idea and I'll mull that idea over for a couple of days. And then I'll start throwing a model together. Depending on how complex the model is, sometimes it only takes 10 or 15 minutes. Sometimes it takes 10 or 15 days. But then once you get the model built, you can check the SWR of the antenna, you can look at patterns, You can kind of determine if it's going to do what you expect it to do, if it's going to be worth building, and then if it is, you can go ahead and build it. Now, that doesn't mean that it's going to work. I've built several antennas that I've modeled that just simply didn't work, and that's not a fault of the software. It's because I didn't model or put into the modeling software key installation factors for my antenna. So things like feed line and proximity to metal structures and trees and that sort of thing. But 9 times out of 10, when you model something and then you build it, the built antenna will very closely follow the model, and it can get you close on wire lengths and dimensions and stuff like that. So anyway, there you go. I hope to do some more modeling videos in the future. I don't see a lot of videos on YouTube about antenna modeling, so I'm going to try and be a resource for that. And if you are a antenna modeler on any software and you have creative input, please go ahead and throw comments in the comment section below, because I have only been using this software for a couple of years and I still have a lot to learn. So any input is appreciated. Thanks for watching.